Hi everyone, in this video I'm going to discuss quasi-Newton methods as well as show some convergence analysis that supports their use. Quasi just refers to approximate the Hessian in some way. That's all it means. So just as some notation, whenever I do a subscript k and it's not obvious that I'm referring what I'm referring to, that just means take that field and evaluate it at xk. So for example, if I give you the gradient, I'm also going to label that with G, and also I'm going to label Hessian with H. And if I do HK, that just means H of xk, GK is G of xk. Newton's method picks our next search direction as the negative Hessian inverse times the gradient, as we discussed in the previous video. And all quasi-Newton is it says, well, take an approximation of the Hessian. We discussed in the previous video that this HK, depending on its behavior, might not give you a descent direction. So let's go ahead and actually show that. So if we take negative the gradient, dotted with pk, that should be a positive value. But if we want descent. So this is just gk, hk inverse gk. Now, if hk has, let's say that gk is an eigenvector of hk inverse, for example, and its associated eigenvalue is negative. Where lambda is less than 0. That implies that the whole thing is less than 0. So it's not moving in the negative gradient direction, and therefore it is not a descent direction. So in general, what we want with this quasi-Newton approach is for this to be a positive definite approximation of HK. And then just some more terminology you might run into: inexact Newton. The idea behind inexact Newton is that we might not directly approximate this HK. So an example here of an inexact Newton method would be, we actually want this expression of HK here, but rather than explicitly solving PK equals minus HK inverse, we actually, so in practice, what you actually want to do is solve HK PK equals minus GK, right? Because you never want to explicitly form an inverse in most cases. And so an example of inexact Newton is, well, okay, I have this expression for HK, but rather than solving it exactly, I only approximately solve this problem. That's it's a small detail, but the main idea here between inexact Newton and quasi-Newton is very similar. In general, every quasi-Newton method is an exact Newton method, whereas converse is not necessarily true. And of course, some people might not use this term. They only refer to quasi-Newton, or they mean them to literally mean the same thing. But the terminology I've run into is this, that inexact is more general than quasi-Newton. Again, that can sort of differ from person to person. Main idea is similar. So now for the convergence analysis that hopefully convinces you that quasi-Newton methods have use in optimization. So back to our problem, we're minimizing phi of x for x in Rn, and we're going to ignore line search for the sake of this video because we want to look at the convergence rate as we are within a basin of attraction of x star. We're close to the minimum. We want to see how our methods behave close to the minimum. And then, of course, we can talk about backtracking later when we're far away and we need to actually find the basin of attraction. But so we're going to assume no line search, or if you like, that just the step length of 1. How fast do we converge to x star? So to do this convergence analysis, I'll switch colors here. I'm going to define HK, h of x, to be x minus h of x inverse tilde g of x. So these are all vector valued quantities, and this h here is actually will be a tensor. But I'll go ahead and drop these tildes in the next step because it'll just clutter things up. So let's expand h around this minimum x star that I labeled here. So x star is the minimizer of phi that we're within the basin of attraction. We kind of know we're going to converge there. We're close to it. Well, this will be h at our kth iterate plus the gradient of h at the kth iterate times ek plus 1/2 ek star ek star h. Sorry. Hessian of lowercase h xk plus c ek, where ek is x star minus xk. Now, what does the gradient look like of this term? So h is x minus so h of xk is xk minus h tilde k inverse gk. So the gradient of h of xk is the identity minus hk inverse hk, right? Because the gradient, the gradient of the gradient is the Hessian, minus the gradient of hk tilde inverse gk. This product rule there. Now also, h of x star is equal to x star because it's a minimizer. So we have x star equals xk plus, also h of xk is xk plus 1 because we defined h of x by this formula, right? That is our update formula. Plus the gradient of hk tilde inverse gk, ek, plus 1/2 ek star. Okay, so I'm just going to rearrange some terms. Sorry. Yeah. So ek is our error term here. So if we subtract xk plus 1 over to the other side, we get ek plus 1. So I'm just going to go ahead and combine steps here. Ek plus 1 is less than or equal to the norm. So I'm just doing standard triangle inequality stuff here. And I'm going to just call this C3. Where I'm going to assume boundedness. We're not going to be super rigorous here, but you can think about it as we have a finite search region. And so, if I have C2 continuity on a compact domain, I have boundedness of that term. And so let's play with some other terms. So, I'm going to play with this term a bit here. So I have the gradient term here. We know a little bit more about the gradient. Let's Taylor expand around xk. And we get that. But this is equal to 0 because x star is a minimizer. Oh no, I want gk in terms of ek. And so the norm of the gradient at the kth iteration is less than or equal to the supremum over y of the Hessian times the norm of ek. So again, I assume boundedness, that's less than infinity. I'm going to call that C2. And so in total, I have that ek plus 1 is less than or equal to C1 ek plus C2 plus C3 ek squared. Why ek squared? Because I pulled this gk, I pulled the ek out, that becomes ek squared, and I combine the two terms. So let's just call that C4. And now let's look at our analysis. So let's look at a few cases. Oh, sorry. C1 hk tilde inverse hk. So case 1, Newton's method. hk equals hk tilde. C1 is then 0 because that's the exact inverse. Inverse times itself is identity. Identity minus identity is 0. So that tells us that ek plus 1 is less than or equal to C4 ek squared. That is quadratic convergence. And this is super fast. Much, much faster than gradient descent. You might say, okay, well, that's just one term. But look at it this way. Let's say we had an error of 10 to the minus 2. Then at the next step, we'll see roughly 10 to the minus 4. Obviously, there's constants in here, so this is obviously not exact. But then on the next step, we get 10 to the minus 8th, 10 to the minus 16th, and so on. 10 to the minus 16th, that is machine epsilon, and so you're basically done at that point. So if you get, basically what this says is if you give me 2 digits of accuracy, well, really 1 digit of accuracy. If you give me 1 digit of accuracy, I get to machine epsilon within 5 iterations, which is a big deal, right? That decreases your error like crazy fast. So ideally, we'd like this, but like I said earlier, if hk is not positive definite, we can't guarantee descent directions and all these things. So Newton's method is what we want to aim for, but we can't necessarily get it in practice. So case 2 is when we have hk tilde does not converge to hk as k goes to infinity. And so, sorry. Well, actually, this is fine. So in this case, in general, that's going to be greater than or equal to some beta for some beta greater than 0. And so our convergence as this goes as beta times ek. And so if beta is, say, 0.1, you get 1 digit of accuracy. And that's fast. But if beta is 0.999, that's really, really slow. So for example, gradient descent, so sorry, this has to be less than 1, right? That norm has to be less than 1 because otherwise you don't necessarily get convergence at all. So gradient descent can be thought of as a quasi-Newton method where you take hk tilde to be the identity. And so you're looking now at the identity minus kth iterative of the Hessian. So if the Hessian there's no reason for the Hessian to be close to the identity, right? So in general, that will be slow. Slow convergence. So what we'd like to do, if we can, is have hk tilde approach hk as k goes to infinity. And this will be the subject of our next video, as a method that actually accomplishes this to some degree. Although indirectly, of what I would call an inexact Newton method within the terminology I mentioned earlier, but it goes along these lines. So the point is here, now I'm going to think of this as a function of k, this constant. And if hk tilde goes to hk fast enough so that c1 of k goes as a constant gamma times ek to the alpha for alpha greater than 0, then in this case we get superlinear convergence, which is fast. So it's not insanely fast like quadratic. So let's say that alpha is 1/2, right? Then that tells us that ek plus 1 goes as some constant gamma times ek to the 3/2 power. And let's consider this case where we're looking at, let's say I get 2 digits of accuracy to you. Then on the next iteration, we get something like 10 to the minus 3, and then 10 to the minus 4. And now you can start to see it kick in. So now, after I get to 10 to the minus 4, I now give you 2 more digits of accuracy. When I get 10 to the minus 6th, I now give you 10 to the minus 9 accuracy, then 10 to the minus 13, and so on. So it's still a nonlinear convergence pattern, which is still crazy fast. And this will be the motivation for Newton CG or Newton Krylov. And I'll circle Newton Krylov because Newton CG is a type of Newton Krylov method, which we'll get into in the next video. And this is the idea I talked about earlier when I was talking about the exact Newton methods. So the idea here is that you don't solve this exactly. You might have an expression for Hessian, but you don't solve this exactly. You solve it up to that estimate, right here. And so you get this superlinear convergence. You don't have to spend too much time solving a linear system. It's really just it's a great way to tackle this problem and this problem. So hope to see you guys in the next video. And then hopefully after that one, I'll sort of get back to quote unquote prototypical inverse problems where we started, deriving, looking at actual PDEs rather than the linear algebra and optimization here. But of course, these are super important components to it because at the end of the day, inverse problems can be boiled down to an optimization problem. Thank you guys for watching.